Hello everyone. Today I am going to discuss this binary adder in MULTISIM and VHDL, where there's full adder, binary adder that started with the half adder that already been discussed with you in my previous lecture. So here is the half adder, where in half adder there are two inputs A and B, and there are two outputs sum and carry, and accordingly the truth table is this, for sum and for carry, and the sum output is A XOR B and carry output is AB. And based on these two expression, this is your logic circuit for the half header. Sum output is A XOR B and carry out is A and B. Now the problem with the half header is that it has only two input. It permits only two inputs. Suppose if we would like to add up 4-bit numbers. Now while adding this first column of the 4-bit numbers, then this A naught B naught will be applied here, and the sum and carry will be recorded. So sum is suppose as naught, and the C naught, the carry out of the first column, will go to the carry as the next column. Now in the next column we need the 3 input, but in the half header it has only 2 inputs. So therefore people have thought of like another adder called full adder, where this full adder accept 3 inputs A, B and C, in and to sum and output sum and carry. So accordingly there are 8 combinations in the truth table. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So accordingly the sum and carry outputs. So to get the minimized expression in terms of either SOP or PES, we'll go for the K map. So for the sum out, this is the K map that has been drawn for the sum out. So the sum out mean terms for which the output is 1 is this one, 0 0 1. So it is 0 0 1, 0 1 0, this is 0 1 0, then 1 0 0, this is 0 1 0 0, and 1 1 1, this is 0 1 1 1. So as you can see here, none of the ones are being mapped. So therefore all these 4 ones are called the prime implicant, and as a result the sum out in terms of SOP, sum of product expression, is A bar B bar C, A bar B C bar, A bar A B bar C bar A B C. Okay, further if we go for the further minimization of this expression in terms of the XOR, we will find it as A XOR B XOR C. Similarly for the carry out, it has the 4 min terms for which the output is 1. So 0 1 1, this is your 0 1 1, then your 1 0 1, this is your 1 0 1, then 1 1 0, this is your 1 1 0, and 1 1 1, this is your 1 1 1. And 3 maps are possible. So this is one map which is BC, then this is another map which is your AC, this is your AC, and this is another map which is AB, this is your AB. So as a result C out is AB, AC, BC. Now based on these two expressions, sum out as A XOR B XOR C and carry out is AB or BC or AC, we'll go to the design of the full adder circuit. First we'll start with it in the MULTISIM. So this is your MULTISIM. In this MULTISIM, this is the workbench where we'll design the circuit, and the circuit is nothing but the A XOR B XOR C and AB or BC or AC. So here for the A XOR B XOR C, we will use 2 XOR gate. Okay, so this XOR gate we can get from here, this TTL. Okay, 7486. So first we'll use the source, binary source. So let be the sources. So digital source, digital this one, digital interactive digital constant. So we'll use one here as A, so another one as B, another one is C. Okay, let me show you. This is your suppose A, this is suppose your B. Okay, so let us put this level as say this is your A switch A. Similarly, this is suppose B, and this is say C. Okay, so C. Okay, then the output here will put it as input here. So therefore, the finally here will be the this is your sum out. So as an indicator, I'll show you this sum out. So the sum outs will use this indicator. Better to use your probe, so a blue probe. Suppose this is your sum. Okay. Then for the carry, 3 AND gates are required. Okay. So for this AND gate, it is 7408. So here I need 3 AND gates. 1, 2, 3, and 1 OR gate. So OR gate is 7432. Okay, 7432. Return I can use A, B, like that. So here I'll use this directly. This A, so it will be suppose A, B, A or B. So this will be your carry. So carry. Okay. Now first one is A, B. So this is your A. This is your B. Then second one is BC. This is your B. This is your C. Third one is your AC. So this is your A already, and this is your C. Okay, let us save it. I'll save it in a folder. Here, MULTISIM I'll make it as FullAdder. So let us put it as FullAdder. Okay, now let us run it. Okay, this is your run or F5. So when we will run, so now see it is 110. So as per the truth table, when it is 1 1 0 sum 0 carry 1. So as you can see, sum is 0 carry 1. Now select all be 0 0 0. So sum 0 carry 1, 0 0 1 sum 1 carry 1, 0 1 0 sum 1 carry 0, then 0 1 1 sum 0 carry 1, then 1 0 0 sum 1 carry 0, 1 0 1 sum 0 carry 1, 1 1 0 sum 0 carry 1, then 1 1 1 sum 1 carry 1. Okay, so that means it validate the your these things circuit. So let us stop here. Now the same will do it in VHDL. Let us put this circuit. So this is a circuit for the FullAdder using these two expression. Okay, now we'll do the same thing in here VHDL. So this is the Xilinx platform where we'll do the VHDL code. Okay, so in the Xilinx, this is the workbench where we'll write the code. So the step 1, go to the file menu, click on the new project. So you have to have a particular folder in which the new project will be saved. So with this new project there will be folder created. Here I have created already within my F drive DBC Spring 2020 and VHDL folder is there. Within that I'll create a folder, say FullAdder. Okay, by the name FullAdder I am creating one folder. So then location it's done. This is this project, and this is just the description. Okay, now the top level source, you can select the different top level source as HDL, schematic, EDF, and here in our case it should be HDL. Then click on the next. So as in my previous lecture I have mentioned, this wizard, this new project wizard, this wizard is for specifying the hardware to be connected with this Xilinx for hardware testing the logic, for hardware testing of the developed or design logic. Now since we are not going to test we are not going to do the hardware testing. Here our main concern is to simulate the logic only, design the logic only. So here there is nothing to do with this. So as in the previous video lecture I have mentioned, so these are the different parameters which can be set for the given hardware. Hardware can be Spartan, Spartan 3, Vertex, different kind of hardwares. So here you can this property and property name and the property value, say evaluation development board. These are different, you see Spartan, Vertex, all those different development boards are there. Then a product category like different, then family, device, the particular device number, then package, then speed. These things actually is not required as we are not going to connect any hardware now. So just keep it. Next. So this is the summary and the project that you have created, and finish. So as you see here, the hierarchy in this design part, design pane of the software. So this is the project name, FullAdder, and this is the hardware family actually that was set, but as I mentioned, there is nothing to do with this, so whatever it is, let it be. Next step is to add a source file for the VHDL program. So just right click on this project, click on the new source, then this new source wizard will open, and then out of this different source type, you have to click on the VHDL module. Then you need to give a FullAdder. So let us give here in my previous class also I mentioned this file name. First of all, it should not be done exactly same as that of the folder name, our project name. Number two, the name given here, file name will be given here, will be the file name for the VHDL program with dot extension, with dot VHD extension. Also, this same name will be the name of the entity in the program, in the VHDL program. So let us give it as simply FA, FullAdder. Okay, then you have to see whether this location is correct or not. Yes, it is correct, and also yet to the project should be saved, and click on the next. So next is the wizard where you will give the in and out, which is nothing but the entities, different entities of your FullAdder, or entities are being defined in terms of the ports. So as you see here, our FullAdder, the different entities are the inputs are A, B and C in, and output are sum and carry. So here you need to put those entities, A in. And in previous class also I mentioned, if it is a single bit, don't click this bus. If you click on the bus, you have to provide this MSB and LS bit. If it is a bus, means more than one bit. Now it's my single bit, so only B, A or B in, then C is also input, and say sum as my output, and carry as my output. So sum as my output, carry as my output. So that's all. These are my properties. So next, so this gives you the summary of the source file that you have created for the VHDL program. So click on the finished. Once you clicked on the finished, the program will appear here. Now, so as you see, under this FullAdder project, this is my source file. This is .vhd, fa.vhd. So this green part that you see here are the command. So the command line start with double hyphen. Okay, this double hyphen means comment line in VHDL. So these are say different companies. You can write your name here. You can type the date will come automatically. This is file name, project name. Then target device, that the hardware device we are not going to use. Then you can type some description, dependencies, whatever. Okay, so these are the command line. Anything green you see here is the command, and command line started with this double hyphen. Next is the VHDL program. As in my previous class I mentioned, the VHDL program always started with the library declaration. So yeah, as you see, this library, common library, is always comes automatically. The standard or default library, which is IEEE default library. So library, the keyword is the library. Anything blue you see here in VHDL program is your keyword or syntax or command. So keyword or the syntax or the command library to declare the library. So library here is IEEE. This use is a keyword or the command. So this IEEE.stdlogic 1164 is the version. .all means all the files or libraries under this IEEE will be incorporated in this program. Again, these are some of the command. Now next part, if you required anything, any other library, then you have to type it here like this way. But for this program, we need not to have any other library. This IEEE all libraries is sufficient. Next part of the program is the entity declaration. So as I have mentioned, in the entity wizard, you have already defined this A, B, C as input, sum and carry as output. It comes automatically. And as I mentioned, the file name is also the name of the entity. So entity is the keyword, entity is the keyword. Along with this entity is FA. This is the name of the entity. As I mentioned, the name of the entity and name of the file, VHDL file, is same, always same. So so entity, the name of the entity is also a keyword. Now port is the keyword to define the different input output ports. So these are the ports, and it started with the first bracket, port A colon, in is the keyword because it is an input, STD logic because we are using this IEEE.std logic, semicolon to terminate this statement. Similarly B, C, sum is out, carry is out. That's all. These are the different ports that you have defined. This you have need not to type, it comes automatically once you declared the port in the port wizard, entity wizard. Okay, and this port bracket was started here and ended here. Then you need to end this entity declaration. Here you have declared the entity, here you are ending that entity. So entity name FullAdder FA, so end entity. Okay, so this is the second part of the program. Third part of the program is the architecture body of the program. Now as you see, this architecture is also the blue, that means it is architecture is also the keyword or syntax or the command for declaring the architecture, and this is the name of the architecture. You can change it. This is just a name, you can change it. For the time being it is behavioral. Okay, the architecture, that is the command architecture or the keyword architecture, name of the architecture, of is also command, of the entity, that is FullAdder FA is. Okay, so now we will write the main part, that is the body or architecture body of the program, which you need to write the code. Okay, so this architecture begins here, and you see this end also, end architecture, the name of the architecture. Since it is begin here, it has to be ended, so it is also comes automatically. In between these you need to code. Okay, so after the architecture has been begin, we can declare a process. So to declare a process, the keyword is process. Okay, so process within bracket, what to process? The inputs. What are the inputs? A, comma B, comma C. Okay, so process is being declared, and for the process no need to give any name. Okay, so process is begin here. Okay, what the process, and end here, end process. Okay, so in between this begin and end process, we will write the process. So what is the process? The sum output, this is less than equal, is, the meaning is assigned. What to assign to the sum? A XOR B XOR C. So A XOR is the keyword or the command, A XOR B XOR C. Statement is being terminated by semicolon. Then carry is assigned with AB, AC, BC. So you have to type within bracket A and B, AB, or BC, B and C, or A and C, A and C. That's all. Okay, so this is the complete program, very simple. So the main part of the program is this only, out of which several things comes automatically. You need to type only this part. Okay, only this part. This is the main part of the program. So this is the behavioral modeling of the FullAdder. Behavioral modeling means where you are explaining the behavior of the circuit or the logic directly. Okay, so you just save it. Then next step is to check whether the given code that you have written is there any syntax error or not. So that means you need to check the syntax. So the check syntax is under this processing part under this synthesize XST. XST means Xilinx simulation tool. So under this you'll see this seg syntax. So just double click on it. It is running. Syntax is being segged. It's going on. It's going on. Okay, seg syntax completed successfully. That means there is no syntax error. So once the syntax has been segged successfully, the next step is to simulate the logic or test the logic. So for which you go to the implementation, simulation, and under this simulation you will see this is the program. Just again you need to add a source for the simulation. So just right click on it, new source. So what you will give now? The test bench. Okay, say FullAdder test bench waveform. So for this is the file name. It has to be added to the project. Then you need to select now the test bench, VHDL test bench. There is no test bench waveform supported by this particular version of this Xilinx. So we will write another program for the test bench. Add to the project is set. Next. So it is goes to the FullAdder program. Yes. This is the summary. Then finish. So now another program VFA_tpw.vhd. So this is again similar VHDL program. This library declaration entity, this comes automatically. Component is being defined. It is a structural programming. Okay. And then these are the signal ABC as an input. Outputs are sum and carry. This is the outputs. Then you can use some system clock also in this program for simulating the FullAdder logic. But since it is purely combinational logic, we will not use this system clock. So let us make it comment, or you can simply delete it. Okay. Then this instantiation of the different ABCs means input and outputs are being done. Then since I am not going to use this clock, so this part also not required, clock process instantiation. Okay, you can delete it. Now coming to the simulation process. So here the purpose is to make some square wave kind of things, or A, B and C, and sum and carry will be simulated. So after the process, wait for the 100 nanosecond. That means it will wait for 100 nanosecond, then wait for clock period by 10. It's not required because we are not going to use the clock, system clock. So now say A is not A. After 100 nanosecond, A will be, suppose A was 0, then A will be 1, not A. Okay. Then you may again give some 1, and in process it will go again after 100 nanosecond, like that it will go on. Okay, it will go on. So every after 100 nanosecond, or you may write here another 100 nanoseconds. So wait for 50 nanosecond. Okay, so that means what will happen? First it will go to, suppose for example A was 0 because it was being initialized with 0. So A is 0, so 0 will be up till 0, 0, 0. It is up till 100 nanosecond 0. Then it will go to 1 for how many times? 50 nanosecond. Then again it since it goes to again 100 nanosecond, wait for 100 nanosecond, another 100 nanosecond it will 1. So for 150 nanosecond it will be 1, and it will go to 0 for 50 nanosecond. Likewise it will go on. So this is the same stimulation process 1 say for A. Okay, in the process. Next, the same process for B. So let me make it 2. So now I am giving it as since previous one is 100 nanosecond, let me make it 50 nanosecond. Wait for 50 nanosecond. Now it will be B. This is just the timing, you can manage yourself. So B, and here I am giving suppose 150 nanosecond. Then for C, so this will be your steam process 3, and wait for C. Now I am putting it as 200 nanosecond. So it will be just arbitrarily I am giving this timing. It's up to you how you give the timing. And here I am putting it as 250 nanosecond. Just arbitrarily. Okay, now save it. So oh sorry, here just a minute, something is wrong, something is 91. Yes, 2 semicolon, let's give him 2 semicolons. Yes, okay, now let's save it. Now this is the TBW, I mean test based waveform program, that is also with data extension VHD. Okay, so now you need to say whether the syntax of this program is correct or not. This is the program for generating the test bench waveform or the square wave kind of things for simulating the logic. So here you just double click on it, behavioral check syntax. It is checking the syntax. Yes, check syntax successfully completed, so that means there is no syntax error. Okay, now in this program this is being assigned. You see, if you expand it, this was the FullAdder program in which this TBW is FA_TBW is incorporated. Now just check on it. Under simulation, you double click the simulate behavioral model. So just double click on it. Simulating the behavioral model of the FullAdder that has been designed here. Okay, so this is the simulated environment. So see, with this you can see, as you can see, it is 100 nanosecond. You see, wait for 100 nanosecond for A you have given. So this in this 100 nanosecond it is 0, and for, you see, as I have given here 100 nanosecond, and wait for 50 nanosecond with your high, and again 100 nanosecond it goes down to 0 to 50. Okay, like that it is going on for A, and in the second I have given 50. You see, in the 50 nanosecond, wait for 50 nanosecond, so this is the 50 nanosecond, like that A, B, C are being created. Now let us see whether my truth table is verified or not. Okay, suppose you at this point A is 0, B is 1, C is 0, so sum is 1, carry is 0. Yes, correct. So next you see A is 1, B is 1, C is 0, so sum is 0, carry is 1, correct. At this point 0, 0, 1, 0, 0, 1, C is 1, so sum 1, carry 0. Likewise it is 1, 1, 1, sum 1, carry 1. So that means it is verifying the truth table. That's it. So it is validating the truth table. You can do lot many things with this. Now just close it. No. Okay. Now the simulation process is verified. The simulation process is done and it verifies the given truth table for this FullAdder. So next is to see the circuit. So again go to this implementation under design, and you see this three small square box with a green at the top means it is setting this as a top level source. Just select it. Once you select it, this processing part will be activated, different processing. Here we will now see RTL schematic of the circuit. So double click on it. So it will give you the logic circuit that has been generated for the behavioral modeling of this. Okay, so it's running. Okay, start with a schematic of the top level block. Let us okay. So this is the top level block for the FullAdder, where these three inputs A, B, C and two outputs sum and carry. If you double click on it, you will see the circuit. This is A, B, C, A, B, A, C, B, C. This is the circuit. And next, you see the technological schematic. So again, this is the technological schematic. This part is the sum part, this part is the carry part. If you double click on it, you will see this circuit with the equation, the sum of product equation. With the truth table. This is the carry output AB. Suppose this is AB. This is your BC AC, and this is your BC. So here it is AB, BC, AC. AB, BC, AC. Truth table, KMF, that KMF. As you can see here, the sum, it is actually being generated using this equation directly. A bar B bar C, A bar B C bar, A bar A B bar C bar, A B C 1, 2, 3, 4 times, and all these 4 terms finally being added. Let me check again this RTL schematic. Here I'll do one by one. This and here as you see, this will also be the AND gate. directly we'll see the sum and carry. Sum and carry the complete FullAdder together. We'll see. This is A XOR B XOR C. Okay, so that's not many things here are there. We'll not do it. So this is how we do. So that's all for the FullAdder in both your MULTISIM. This is your MULTISIM. Like this, you just change it. Okay, so this is your MULTISIM, and this is your VHDL code, and this is the code for the test bench from where this timing you can play with this timing yourself. Okay, let's stop here. Thank you very much for listening.